We are going to see a solution to exercise 2 from chapter 2 of Walter Rudin's Principles of Mathematical Analysis. We will be proving a very important foundational result, that the set of all algebraic numbers is countable. A complex number z is said to be algebraic if there exist integers a sub 0, a sub 1, up to a sub n, not all 0, such that a sub 0 plus a sub 1 times z plus ... plus a sub n times z to the power n equals 0. Prove that the set of all algebraic numbers is countable. Please see the hint. For every positive integer n, there are only finitely many equations with n equals n plus the absolute value of a sub 0 plus ... plus the absolute value of a sub n. For a polynomial of degree n with integer coefficients a sub 0, a sub 1, ... a sub n, there exists a natural number n equals n plus the absolute value of a sub 0 plus ... plus the absolute value of a sub n. Such a number n can also be associated with some other polynomial. From the hint, we skip the verification. We observe that the collection of such polynomials for a given n is finite. Every rational number q equals m divided by n for some integers m and n is a 0 of the polynomial nx minus m. Hence, the set of rational numbers is a subset of the set of all algebraic numbers. Let p of x be a polynomial of degree n with integer coefficients a sub 0, a sub 1, ... a sub n, such that n equals n plus the absolute value of a sub 0 plus ... plus the absolute value of a sub n. Then e sub n, defined as the set of all such polynomials p of x, is finite. Now for each n, collect all zeros of each polynomial in e sub n into a set, say, a sub n equals the set of all complex numbers z, such that p of z equals 0 for some polynomial p of x in e sub n. Since each polynomial has finitely many zeros, and each e sub n contains finitely many polynomials, the set a sub n is finite for each n. From a corollary to theorem 2.12, the union from n equals 2 to infinity of a sub n is at most countable. Notice that this union from n equals 2 to infinity of a sub n is precisely the set of all algebraic numbers, and hence it is countable. Moreover, since the set of rational numbers, which is countable, is a subset of the set of all algebraic numbers, the set of algebraic numbers is indeed countable. The reference used for this exercise is W. Rudin's Principles of Mathematical Analysis, 3rd edition.